Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's see, Steve has been at UW working with Susan Eggers first, and then more recently Mark Oskin has been advising him. He and Mark have started this WaveScalar project that I think we'll be hearing about today. Steve held Intel Fellowship and did some work at Intel. He actually had a brief sojourn into ubiquitous computing in the middle of his grad student career. I also just learned recently Steve is a budding ping pong player. Unfortunately, we don't have our tables set up here, so we can't try him out that way. Get the true test of his worth.
That's right. Well, thanks. To lower the handicap. So thanks for having me today. I'm going to talk today about rethinking processor and system architecture. And my talk is going to come in two parts. So the first part of the talk, and most of it, is going to be about this WaveScalar project that I've been working on at the University of Washington. And the goal of the WaveScalar project was to design a scalable processor architecture that could address the challenges that face processor designers today, while at the same time achieving very good performance on a wide range of different workloads. After I've told you about WaveScalar, I'm going to shift gears a little bit and talk about how the same technology trends that led us to explore an architecture like WaveScalar are also going to lead to fundamental changes across all aspects of how we design computer systems. So to motivate things today, I'm going to give you a brief retrospective on
It's catching up.
That's right. Exactly. Come on. Wow. Clearly, I should be using a Windows machine instead of a Mac. Let's go. Okay. So, well, it is PowerPoint. Okay, so I'm going to give you a brief retrospective on what I'll call the good old days of computer architecture. And so I put up this graph, and this is the clock rates of 4 different families of architectures from 4 different manufacturers from the late 80s to a couple of years ago. And this is one of the things that was so great about the good old days, is that we had this ever-increasing and ever exponentially increasing level of performance that these processors could deliver. The other thing that was nice about the good old days was that during this era, almost every processor that we built used something called the von Neumann model of computation. And also, almost every processor we built was built around the same basic design. And as a result, we got very, very good at building this style of processor. Now, you might have noticed that all these curves end in about 2002. And because that's because in the later part of that year, something cataclysmic happened. And all these curves, which had been increasing exponentially, tipped over and became linear. Now, there are a bunch of reasons for this. I'm going to focus on 3 of them today. The first was one of complexity. And as we built these ever faster single-threaded processors, the complexity of the processors increased exponentially. And we got to the point where sort of the next generation of processors was going to be so complicated that it was almost infeasible to design and verify that they were going to work properly. The second difficulty was one of clock scaling. So during the good old days, our favorite trick for making processors faster was to increase the pipeline depth and use that to ratchet up the clock rate. And it became clear that for a variety of reasons, both of those trends had more or less run out of steam. The third problem was one of area scaling. And the thing to realize about this graph is that this is not plotting the number of transistors that are available on a particular piece of silicon. That number continues to increase exponentially, and we think it will continue to do so for the next 5 to 15 years. What happened here was that we didn't know how to take those transistors and convert them into a commensurate increase in performance. We didn't know how to spend them to make our processors faster. So industry has seen all these trends coming, and they've responded in a very simple way. And that is to build something called a chip-multiprocessor. So to build a CMP, you take the von Neumann style processor that you already know how to build, you shrink it because technology will allow you to do so, and then you stamp out multiple cores on a single piece of silicon. The resulting processors are low complexity because you just have to design and verify one of those cores. They're scalable because as more transistors become available, you can stamp out more and more of the cores. And there's also hope that they might be fast, because in this case, if I can break my program up into 4 threads, I can run them in parallel and get 4 times the performance. Now, it turns out that things aren't quite so rosy with CMPs, and there are actually some pretty significant problems that arise when you design processors this way. The first is that they're hard to program. So breaking your program up into threads, using locks appropriately to get the correct result, and also debugging these multi-threaded systems are all very difficult problems that we don't have good answers for. The second problem is that they don't scale practically. So if you look at the number of threads that are available on the desktop, it seems that there's about 4 to 8 threads available. And so that's fine if you have, say, a 4-core machine like I've shown here, but in a few years, Moore's law is going to deliver us a 16-way CMP, and in a few more years, we'll have a 64-way CMP. So how are we going to utilize that style of architecture? The third problem is one of inflexible allocation. And the difficulty here is that the granularity at which you can assign hardware resources to a particular computation is very tightly constrained. So the correct way to program this processor is to have 64 threads that are all the same size, and that size should precisely match what can fit nicely onto one of these cores. If your program would better be broken up in another way, say one larger thread and some smaller threads that need fewer resources, there's no way to exploit that kind of organization on this style of processor. The final problem is that these processors really can only exploit coarse-grained thread-level parallelism. So if my program has a lot of fine-grained parallelism or a lot of instruction-level parallelism, there's no way to exploit that kind of parallelism on those kinds of parallelism on this style of machine. So the goal of the WaveScalar project was to develop an architecture that was low complexity and scalable, just like the CMP, but that got around some of these problems that these CMPs have. So what is WaveScalar? Well, WaveScalar is a new, scalable, highly parallel processor architecture. It's not a CMP at all, and in fact, it differs from a chip-multiprocessor in 2 essential ways. The first is that it uses a fundamentally different algorithm for executing threads than the conventional CMP does. And the second is that it's going to organize its hardware very differently. So with that in mind, I'll give you a brief overview of what I'm going to talk about today. First, I'm going to describe to you WaveScalar's data flow execution model, how it differs from the more conventional von Neumann model, and also how WaveScalar had to overcome a fundamental limitation of the von Neumann model, of the data flow model, in order to make it a useful architecture. Then I'm going to talk about the WaveScalar hardware design and give you an idea of what a WaveScalar processor looks like. Then I'm going to describe how we evaluated that design and figured out which WaveScalar processors would be worth building. Then I'm going to talk about how WaveScalar can exploit some of the features of its underlying data flow execution model to accomplish things that a conventional chip multiprocessor cannot. And then finally, I'm going to talk about how those technology trends that led us to WaveScalar will lead to changes elsewhere in the system. So let's jump right into the execution models. So every core in a von Neumann processor, in a CMP, uses something called the von Neumann model of execution to execute a program. And the key piece of the von Neumann model is a program counter that points to the current instruction in the program. And at each step, we're going to execute that instruction, and then we'll increment the program counter so it points to the next instruction. Because of the program counter, the von Neumann model is fundamentally centralized because that single program counter controls all aspects of execution. And it's also very sequential because as it steps from one instruction to the next, it generates this long linear sequence of instructions that defines the execution of the program. If we look at the data flow model that WaveScalar uses, we'll find that it varies in almost every respect. So WaveScalar is not a new idea. It was invented in the mid-'70s by a guy named Jack Dennis. And in data flow, instead of being represented as a sequence of instructions, programs are represented as a data flow graph. Programs in a data flow system fire according to something called the data flow firing rule, which states that the instruction should fire when the data arrives. So here we have this add instruction that takes 2 inputs. When the first input arrives, we won't do anything because we're still missing 1 input. And when the second input arrives, we'll execute the instruction and generate the result and send it on to the other instructions that require it. The data flow firing rule allows the instructions in the program to act independently of one another, so there's no need for centralized control. And it also means that all of the instructions that have their inputs available can fire in parallel. And as a result, the data flow model is very, very good at expressing parallelism. And in fact, when people built these machines on the 80s and early 90s, they got very, very good performance. So the question then is, where are all the data flow machines today? And it all comes down to how the data flow model deals with memory. So to illustrate how this is a problem, we're going to take a look at this very simple piece of code executed in both execution models, the von Neumann model first and then the data flow model. We're going to write a value into an array, and then we're going to read a value back from the same array. And the thing to realize is that these two operations have to occur exactly as they're written if we want the program to compute the correct result, because if I and j are both equal to 0, then those two addresses will be identical. So in the von Neumann world, things are pretty simple. We'll have a sequence of instructions to compute the addresses, and then, to guarantee that ordering constraint, we'll just write the store first and then follow it by the load. And the von Neumann model guarantees that things will occur exactly as we've written them. In the data flow model, we have a different picture. So here we have the data flow graph for the same computation. And what will happen first is somewhere off the top of this picture, some other instructions will generate the values for a, I, and j. Those will provide the inputs to these two multiplies, which will execute providing the remaining inputs to the two add instructions. And then on the third cycle, something interesting happens. And because the address computation for the load is simpler than that of the store, the load is actually going to fire first, followed by the store on the next cycle. And so now these two memory operations have executed in an incorrect order, and that's going to lead to an incorrect result for our program. So it turns out that this inability to order memory operations was really Dataflow's Achilles heel. If you can't order the memory operations, that means you can't support imperative languages like C or C++ or Java. And to get around this, the people who designed these data flow systems when they were building these machines required that you use these special purpose, purely functional data flow languages for writing your programs. And so this is a huge problem, because it means if you want to run a program, say Microsoft Word, you have to rewrite it from the ground up in this purely functional language, which looks very different from what most developers are used to dealing with. So the bottom line here is that if WaveScalar is going to be a useful architecture, it's going to have to solve the data flow memory ordering problem. And in fact, it's this ability to order memory operations correctly that's going to set WaveScalar apart from previous data flow instruction sets. So what would a solution to this problem look like? So we want to order the memory operations, but we'd like to provide just enough ordering, because we also want to preserve the parallelism that data flow is so good at expressing. We want to preserve as much as possible our performance. And so we need to be very careful when we try to solve this problem. So the solution that I devised that solves the data flow memory ordering problem and does a pretty good job of preserving parallelism is called wave-ordered memory. Wave-ordered memory works by having the compiler provide 3 annotations on each memory operation in the program. The first annotation is called a sequence number, and these numbers are unique across the memory operations, and they have the property that on all paths through the control flow of the program, they're always increasing. So in this case, it will either go 3, 4, 7, 8, or 3, 4, 5, 6, 8, depending on which way the branch goes. The second annotation is called a successor number, and this is just the sequence number of the next memory operation in program order. And in cases where there's ambiguity, for instance at this branch point, we'll just write a question mark. The third annotation is called a predecessor number. And this is just the sequence number of the previous memory operation in program order. And again, if there's ambiguity, well, we can write a question mark there as well. These instructions can fire in more or less any order according to the data flow firing rule. And they're going to send their request to the memory system along with these annotations. And the memory system is then going to use those annotations to reorder the memory operations to make sure that they occur in the correct order.
How do you do these annotations when there are loops in the program?
Wait a couple slides. So I'll give you an example of how this works in practice. So we'll assume the control is going to take the right-hand path. And remember, things can execute in any order. But to keep things simple at the beginning, we'll say that the top load fires first. And it tells the memory system, I'm operation number 3, and the next memory operation you should expect to see is operation number 4. If operation number 4 fires next, it'll tell the memory system, I'm operation number 4, but I don't know what's coming next because I'm at a branch point. Now to make things interesting, we'll say that this final store fires next, and it'll tell the memory system, I'm operation number 8, but I don't know what came before me because I'm at this join point. And at this point, the memory system is sort of stuck because it doesn't know what came in between operations number 4 and 8. When the final load fires, it's going to resolve that ambiguity because its predecessor number matches up with the sequence number of an operation that we've seen, and its successor number matches up with the sequence number of another memory operation that we've seen. So at this point, we have the memory operations in the correct order because we have our sequence numbers that are increasing. And we also know that we're not missing any memory operations because we can build this sort of linked list between these predecessor, successor, and sequence numbers. In hardware, the way that we exploit this information is we just build a store buffer that accumulates those memory operations and applies them to memory as it determines that it's safe to do so. Now, as you pointed out, we have to deal with loops. And that scheme only works if there aren't any loops. So to deal with loops, we're going to introduce the notion of a wave. And a wave is just a loop-free section of the control flow graph. So the piece of code on the previous slide is a wave. I've shown it here as the body of a loop. There's another wave that comes before the loop, and a third wave that follows after the loop. We're going to assign each wave, each dynamic instance of a wave at execution time, a unique wave number. And those numbers are going to increase as execution proceeds. We're also going to say that every value that flows through a WaveScalar program carries with it the wave number of the wave that it belongs to. And we'll introduce some special instructions that are going to manage those wave numbers and keep them synchronized. And all that they'll do is increment the wave numbers on the data values that pass through them. So in this case, we'll start off perhaps before the loop in wave 0. We'll go through the green bar once, and the first iteration will be on wave 1. We'll go around the back edge and through the green bar again, and the second iteration will be on wave 2. So these wave numbers provide ordering among the waves of execution in the program. And the sequence numbering scheme on the previous slide provides ordering within a single wave. And so combined, they provide the total ordering on all the memory operations in the program that we need to support these imperative programming languages. There's a few other things that I'll mention about wave-ordered memory. The first is that the annotations on the memory operations essentially summarize the control flow graph of the application. And WaveScalar is actually the first instruction set to provide this sort of explicit structural information in the ISA directly. The other 2 points, I don't have time to talk about it in any great detail. The first is that there is a mechanism for exploiting some parallelism in the data or in the wave-ordered memory interface. In particular, we can allow consecutive memory operations to be reordered relative to one another if the compiler determines that it's safe to do so. The second point is that there's an alternative solution to the data flow memory ordering problem called token passing. It's been around for quite a while. We've done a head-to-head comparison between the two, and it turns out that wave-ordered memory preserves about twice as much parallelism as the token passing solution. So we do a better job of preserving parallelism while providing this ordering that we need. So at this point, we have almost everything we need to replace a conventional chip multiprocessor system. We have the data flow execution model for executing our threads. We have a von Neumann style memory interface and wave-ordered memory. The other 2 pieces we need are a coarse-grained threading interface, which we provide, but I don't have time to talk about today, but it's very similar to something like p-threads. And then finally, we also provide a lightweight synchronization mechanism that lets us build very lightweight locks and integrates very nicely into our data flow execution model. So with all that in hand, I'm going to shift gears now and talk about the WaveScalar hardware design. Go ahead.
So in those collapsed sections, is that where I would learn how multiple threads are going to communicate through the memory system without having, while having the synchronization be well defined? Is that what you're collapsing away?
Yeah, that's what I'm collapsing away. We have a memory barrier instruction that interacts with the wave ordering system.
So is there basically another scalar value that tells you which thread you're on, and that's what?
Yeah, each data value is actually also carries with it the thread ID of the thread that it belongs to also, and value. Yep.
Okay.
So I'm going to talk about the WaveScalar hardware design and give you an idea of what a WaveScalar processor looks like. I'm going to show you that the design is scalable, low complexity, and also pretty flexible. So if we think in the abstract about how we'd like to think about building a WaveScalar processor, kind of what we'd like to do is build a processor where each instruction in the program had its own dedicated ALU. This would map very nicely onto our kind of abstract picture of the data flow execution model. Practically, of course, we can't afford to build so many functional units. What we can do is we can build a smaller number and then find a clever way of reusing them so that it appears that each instruction has its own dedicated ALU. The way that this will work is it will build a big array of processing elements. And this is a cartoon of a WaveScalar processor. And we'll take the working set of instructions for an application, and that portion of the data flow graph, and we're going to map it onto this array of processing elements. The instructions will remain there for hundreds or thousands or even millions of executions, communicating with other instructions that are also mapped into the array. And then as the working set of instructions evolves, we'll kick out some of the old instructions that are no longer needed and map in their place some instructions that have been activated more recently. I'll go into some detail about how we design this thing. It's a very hierarchical design, and I'll start at the very bottom. So the smallest piece of a WaveScalar processor is called a processing element. It's a very small, simple silicon structure. It has about 500,000 transistors, and has a 5-stage pipeline, and also holds about 64 static instructions, although only one of them can execute on a given cycle. The key components of the processing element are the input queues that I've shown here in blue. This is where the data values wait to be consumed by the ALU that I've shown in red. It's also where the data flow firing rule is implemented. Go ahead.
When you say it holds 64 instructions, do you mean it has a instruction set architecture of 64 instructions, or do you mean there's 64 dynamic instructions that you can store in there?
64 static instructions that I can store there.
And so that's the language at this level is what you're saying. That's the
there are many more than 64 different
of
instructions. There's a buffer of 64 instructions.
Ah,
Yeah,
okay, thank you.
essentially. This is where the matching rule is implemented, and then the data values leave the processing element via the output queue that I've shown here in that cream color. We take two processing elements, combine them into what we call a pod, so we have two PEs in a pod. And within a pod, the two processing elements... Talk to my advisor. Within a pod, the two processing elements are completely disjoint, except that their bypassing networks are conjoined. And what that allows us to do is get back-to-back execution of dependent instructions within a single pod, and that turns out to be pretty important for overall performance. We take four pods, we combine them into something we call a domain. Within each domain, each processing element uses a broadcast bus to communicate with the other processing elements in the same domain. Take four domains, combine them with a conventional L1 data cache, a store buffer that implements the wave-ordered memory interface, and a network switch to communicate with other parts of the processor. And this is what we call a cluster. And this is sort of the basic tile of a larger WaveScalar processor. To build larger processors, we stamp out multiple clusters to cover as much silicon area as we'd like to spend. We surround the entire thing with a banked L2 data cache. For long-distance communication, we use dynamic routing over a grid-based network formed by the network switches in each cluster. The design I've shown here will hold about 32,000 instructions. It occupies about 400 square millimeters of silicon in a 90 nanometer process, and it has a clock rate of about 1 gigahertz, or if you know what an FO4 is, it has a cycle time of about 22 FO4. This architecture turns out to have some pretty nice properties. First off, it's low complexity and scalable for essentially the same reasons that the CMP is. And that is that we have these basic silicon building blocks that we replicate many times to build the whole chip. So we take the processing element, we stamp it out to build a domain, we take the domain and stamp it out to build a cluster, and we stamp out the cluster at the highest level. The design also allows us to exploit a range of different styles of parallelism. WaveScalar can execute coarse-grained threads, fine-grained threads, and it's also very good at exploiting the instruction-level parallelism that the data flow model is very good at expressing. The final point is that it allows for very flexible allocation of resources among the threads. So in WaveScalar, it's very easy to allocate the entire array of processing elements to a single thread. Alternatively, you can allocate one large thread and four smaller threads if that is a better match for your applications. Or you can break it up in a completely irregular way if that's the best match for what you're doing. The key difference here between WaveScalar and a conventional chip multiprocessor is that the unit of hardware allocation in WaveScalar is one entry in that instruction store at each processing element, at a single processing element. So we can actually allocate just a very thin sliver of hardware to a particular thread, and the hardware and the execution model don't have any problem with that.
You sort of just have like these, continuing with the iCache analogy, I mean, you're basically controlling different iCache miss rates. Like you have to allocate more area to the thread, then it has a lower iCache miss rate, whereas if you give that same thread a tiny little area, then it just have to suffer higher iCache miss.
That's exactly right.
You just have to take the data flow graph and map it onto pieces of hardware.
Right.
If you allocate more hardware to it, then you can do a wider stages.
Yes. So you also, so you allocate more hardware, you get more performance.
So is the relative cost of an iCache miss greater here than on a conventional iCache?
It is. So the cost of kicking something out is higher. The cost of bringing something back in is also higher. So the bottom line here is that if you thrash, your performance will go down pretty dramatically, more so than it would in a conventional processor. So we go to great lengths to keep that from happening.
So what is the abstraction here for saying that these are the instructions that I want to execute somewhere, and there's this virtual memory kind of thing that's deciding which instructions actually get to reside in there.
Right.
So where in this picture is the instruction cache?
The instruction cache is distributed. So each one of those little instruction stores at each processing element is essentially a piece of the whole instruction cache for the processor. And that's backed by the L1 data caches where the instruction data can live when you write it out, and then also by the L2. But there's no conventional centralized iCache.
Right. So you just have that local cache, and if you overflow that, where does it go?
So what happens is at compile time, the compiler generates an assignment of instructions to particular processing elements, and it's allowed to oversubscribe them. So for instance, they can hold 64. It might assign 1,000 instructions to a particular PE. And it places them, keeping in mind the various data dependencies between them to try to reduce communication costs. Then at runtime, we use an LRU algorithm to decide at a particular PE which instructions are mapped there at a particular moment. And they come in and they'll remain there hopefully for a long time so we can amortize this larger cost of bringing them in and then kicking them out and then bringing them back in.
Actually, so when you really lose, you're talking on this global grid co-patch.
Say again?
I was just saying, you have finite storage on one of these local PDs.
Right.
Right. You need to have more instructions than that. You've got to put them somewhere else. And
Right.
That's,
Right.
That
They're out in the L2s, or
they can be written out to memory in the L2 and to the rest of the memory hierarchy, and then they'll be brought back in when they're triggered again. Yep.
How is the assignment of a thread done to one of these individual processing elements?
It is so that at runtime, the set of instructions that's actually mapped onto a particular PE is handled by a software mechanism. So when you need to place when you send in a message to an instruction that isn't there, essentially the operating system or the firmware gets invoked and tells you where that instruction should go. That operation is pretty cheap because it basically just does a lookup to figure out where the compiler said that instruction should end up. And then it's mapped in. You just send a message to the PE saying load this instruction, and then it does the rest.
So you have to decide the shape of those threads, sorry, John, at compile time?
You need to decide roughly the shape of the threads, but there's also a pretty strong dynamic aspect. So a placement for a particular thread might say, start here and, occupy all of this. But depending on what the working set of instructions is, only parts of it may be active at once. And you can assign multiple threads to the same area in the grid, and they'll sort of duke it out.
So it sounds like the flip side of that is that any given thread, any given instruction only has one place in the entire processor can live, so you really have a one associative instruction cache.
So that's...
Oh.
Right. So it's more like a 64-way instruction cache, or 64-way set associative iCache.
So how specific is the compiler's job to the particular version of the WaveScalar architecture it's compiling for? And like if you were to take a program binary and then try to run it on like a future version of an architecture, would that be possible?
It would be possible. So one of the nice things about our system is that all of that placement information is more or less a hint. If you map it on to an array with different geometry, the performance will just go down if you got the placement wrong. You can also imagine, and actually our current system does this to a certain extent, when the compiler generates the placement, you can generate sort of a archetype of placements for that piece of code that say these are the communication patterns, and then at load time you can analyze it and take a look at what hardware you actually have available and decide exactly how things should be broken up. So the expensive part of the analysis is doing this clustering business of figuring out which instructions should be nearby to one another. Once you have that, breaking things up is pretty easy. And so that's something you could do at load time if you wanted to have more independence from the hardware. Okay, so this is what the architecture looks like. I have a brief demo, which will hopefully give you some intuition about how execution behaves. So this is a 4-cluster processor. Each of the clusters is broken up into 4 domains. And then each of these black boxes represents a different processing element. As execution begins, a bunch of instructions are mapped in, and it turns some of the processing elements red. These black lines represent different communication arcs among the instructions. So there's 3 things to notice here. The first is that this looks qualitatively very different from what you would see if I showed you sort of a similar picture of a conventional von Neumann processor, where you would see instructions floating from one end of the pipeline to the other. Here, the instructions are remaining stationary, and the data values flow between them. The second thing to notice is that because the instructions remain stationary, we can optimize their placement, which is what I was just talking about, to minimize communication costs. So here, most of the communication actually occurs within a single domain, and for this particular sequence of execution, there's actually no communication that crosses a cluster boundary. And so we do a pretty good job of localizing communication. The third thing to notice is that although it's not particularly obvious here, there are actually 16 threads running here at once, even though there are only 4 clusters. And this speaks to WaveScalar's ability to pretty flexibly allocate hardware resources among the different computations. And this is a 16-way threaded FFT, if you're curious. Yep.
So I think I'd like to rearrange that question I asked earlier that was sort of silly, which is when I asked about the associativity of the cache, I realized that, yeah, okay, now I understand that there's 64-way associative and that you might have 64 instructions in the same PE.
Right.
But the downside is if a bunch of instructions do gang up on that one PE, unlike an instruction cache where there's sort of no cost to that until you go
right. Right.
Here you're splitting the compute time of that PE.
I'm saying if the compiler assigns 1,000 instructions to one PE, and then it turns out you actually need
all of them
active at once.
Right.
Well, that would be true on a 64-way. That would be a problem for a 64-way set associative instruction cache as well. But even if the compiler only assigns, even if only 63 of them have to be active with a regular iCache, there's sort of no cost for that as long as you're below the threshold, as long as you don't thrash. But here, if you're below, if you have 63 instructions that are actively using one PE, the problem is they also have to share the ALU on that.
Right. Right. So actually, our placement system takes that into account. So the way that it works.
So that's why load time investment is important.
Well, actually, this is in the clustering part. So what the placement system does is we profile it to figure out which communication paths are important, and then it generates little sequences of instructions according to a depth-first search. The nice thing about the depth-first search is that it guarantees that those little strings of instructions can't execute in parallel because there's a data dependence between them in a little chain. So if you map those all into one processing element, you know that they're not going to fight over the functional unit resource.
And then if you map another thread, you add some constant offset to sort of shift it into...
Right, right. So our thread placement algorithm is like here, and then we go over by like a prime number and wrap around and so forth. So it spreads out.
Because the structure is repeating, you're not breaking up the clustering things you learned from the
right.
The compiler.
Right. Okay. Here's the demo. Okay. So the last thing that I'm going to say about the hardware is to just put our design in context with some previous data flow hardware efforts. And there's a huge number of them. This is actually a pretty small sample of all the machines people built. As I said, it got its start in the mid-'70s. People built things more or less continually until the early '90s. And the biggest thing that changed across these implementations is how they implement the data flow firing rule. That's sort of the key piece to having an efficient data flow machine. In that respect, our most direct ancestor is something called the Manchester machine that was built in England in the mid-'80s. And if you take the Manchester machine's processing element, you update it for modern process technology, add a wave-ordered memory interface so you can execute imperative programming languages, you have a very, very rough sketch of the WaveScalar architecture. So on the hardware side, WaveScalar's contributions are in demonstrating that we can build a scalable data flow architecture in modern process technology. And as I'm going to show you in a few slides, that it can get very good performance.
Why Manchester? Starting point.
Kind of by accident. I mean, we didn't choose that machine. So the thing that changed from here on down was the data flow firing rule can be somewhat expensive to implement. And so to reduce, it's basically a synchronization operation. So to reduce the synchronization cost, you want to make the synchronization less frequent. So that's what happened as you go down this list, is they got kind of the operations in the data flow graph got bigger. So you had to schedule less, or had to synchronize less frequently. So the reason that WaveScalar doesn't have a coarser-grained data flow firing rule is that we're going after these imperative programming languages that have, if you look at sort of the spectrum of parallelism they have a small amount of instruction-level parallelism. And there's a big gap. And they have a bunch of very coarse-grained threaded parallelism if you have a multi-threaded program. So we can't kind of play across this whole spectrum, whereas these other machines that used these special-purpose data flow languages, those data flow languages provide this nice spectrum of parallelism. Kind of anywhere you look, you'll find good parallelism. And so they could ride that curve back and forth to build the architecture that best suited their currently available technology. We're a little more constrained because we're after the particular class of applications, so we end up playing down here. These up here were woefully inefficient. They use something called CAMs, or content addressable memories, which are big and power hungry and generally a bad idea. So
don't you have the same problem with doing associative match in your tokens?
So after starting with the Manchester machine and on down, all of them well, that's not quite true. Manchester and WaveScalar, at least, use a hashing scheme. So when the data value arrives, you compute a hash of, in our case, the wave number, the thread ID, and the instruction, the destination instruction, and use that to index into the table. And then you can just check. So, okay. So I'm going to shift gears now, now that we know what the architecture looks like, and talk about how we evaluated it. The first thing I'm going to talk about is how we mapped WaveScalar's design space to take a look at which designs are worth building. Then I'm going to show you that it's scalable and also present a comparison to some other CMP architectures. So before I can do any of that, I'm going to talk very briefly about how we arrived at our performance measurements. So we use a cycle level simulator to get our performance measurements. Then we run a range of different workloads on that simulator, including parts of spec-int and spec-fp, also splash2, which is a multi-threaded scientific set of workloads, and MediaBench, which are a bunch of media applications. Our toolchain currently uses a binary translator that takes conventional von Neumann-style binaries in the alpha instruction set and converts them into the WaveScalar ISA and executables. And we report all of our results in alpha instructions per cycle. So what this means is that we ignore the WaveScalar specific instructions that are added during this binary translation process, so that our AIPC numbers are directly comparable to the IPC numbers that you would see in more conventional processors. We also have a synthesizable Verilog model that's going to provide area and delay measurements that I'll talk about briefly. So the first question that I'm going to address is how we explored the WaveScalar design space. So there's a whole bunch of parameters that define a particular instance of a WaveScalar processor, things like the number of clusters, the number of domains, the number of PEs, the number of instructions per PE, and so forth. So the design space is very, very large. To make matters worse, there's no good intuition about how these different parameters should affect bottom line performance. If I was building a von Neumann processor, I could look at sort of the history of von Neumann designs and get a pretty good idea about how turning some of these knobs would affect how bottom line performance would react. Here we're more or less flying blind. So the question then is, how do we find the good WaveScalar processor designs? And there's two choices. We can search by hand. That'll work. It'll take a long time, and there's a chance that we might miss something. Or we can try to do a complete and systematic search of the design space. And that's a little more challenging because our design space is so large. But that's the path that we went down anyway. And so our first task was to try to constrain that design space. So to do that, we started off with our synthesizable RTL model. And we used that to build an area model for WaveScalar processors. So you give this model the settings for all these different parameters, and it'll give back to you an area in square millimeters of that processor if we were to actually build it. The RTL model also gives us our cycle time, which is 22F04, and we can fix that. And we can also fix an area budget at about 400 square millimeters, because that's about as large a processor as people can manufacture today. We'll also apply some common sense rules. So there are some designs that you can look at and just say, I can build a design that's strictly faster and no larger, or a design that's strictly smaller without giving up any performance. So we just throw out those kind of nonsensical designs. And then finally, we're just going to focus on the area critical parameters, the ones that have a strong effect on the output of this area model. So if you do all of that, it turns out there are 201 reasonable WaveScalar designs, and that's a small enough number that we can just simulate all of them. And so here are the results for Splash2. So each one of these green dots is a different WaveScalar configuration. The horizontal axis is the size of the chip in square millimeters. The vertical axis is our performance in AIPC. So the good designs are up and to the left because we like designs that are small and fast. If you look at the upper kind of left fringe of this set of this cloud of points, we have what I'll call the Pareto optimal design points. What it means for a design to be Pareto optimal is that there's no other design that is both smaller and faster. So you can think of this as, for a particular area budget, this is as much performance as we can get. By studying these Pareto optimal design points, we can learn some interesting things about WaveScalar. The first is that the architecture is very scalable. So if you look among these Pareto optimal points, you can find points that are a factor of 7 apart in both the area they require and the amount of performance that they can deliver. And so this is really exciting because if you remember at the beginning of my talk, I mentioned that this is one of the challenges that we were facing as architects, was how to convert transistors into a commensurate increase in performance. And so WaveScalar does a pretty good job of doing that. Good.
Where does the alpha fall on this? How many square millimeters?
That's on the next slide. Okay. The second thing that we can look at is what I'll call the area efficiency of WaveScalar. And this is just the performance per silicon area. So for WaveScalar, the smaller clusters have an area efficiency of about 0.07. The larger designs have an area efficiency of 0.05. And we can compare those numbers to the other processors that people have built. For instance, the Pentium 4 has an area efficiency of between 0.001 and 0.013, depending on the application. The Alpha 21264 has an area efficiency of 0.008, so about an order of magnitude more efficient than they are. And the most interesting comparison is actually to this processor called Niagara. It was recently released by Sun Microsystems. This is an 8-way chip multiprocessor. Each of those cores actually runs 4 threads, so this is actually a 32-way threaded processor. And the best comparison here is to this larger set of designs. Niagara is a pretty good-sized chip, and we're about a factor of 5 more area efficient than the Niagara design. Yep.
This is a strange comparison. You're looking at instructions per cycle, not work per second.
The clock cycles are comparable across all of these, or they've been scaled to be so.
So you scale that.
Yeah.
So it's really not measuring IPC per millimeter.
So it is under, so you're right, it should perhaps better be labeled as bottom line performance per square millimeter. But it's difficult to put a number into the divisor, so we scale the clock rate to get the numbers instead. Okay. So the last piece of performance results that I'll present is a comparison to a range of other multi-threaded designs. So here we have a range of designs on 3 different workloads from the Splash 2 benchmark suite. WaveScalar is the first one. SCMP is a chip multiprocessor of our own design that's built to fit as many cores as possible into a single piece of silicon. The other designs we've taken from the literature. So SMT8, CMP4, and 2, and Ekman are designs that other researchers have proposed and evaluated and tuned for these same set of applications. So to make these comparisons, we've had to normalize those results from the literature. And so the comparison isn't perfect, but it's good enough to show the broad trend, and that is that WaveScalar outperforms the other designs by a pretty wide margin. For the designs from the literature, it's hard to say why exactly they perform the way that they do. We don't have access to their simulator. But for SCMP, we do have access, so we can say something more authoritative about that. Turns out there are 2 things that account for the performance gap between SCMP and the WaveScalar processor. The first is that SCMP uses a broadcast bus for coherence traffic and memory traffic, and as more cores are added to that bus, it becomes saturated. The second thing that's going on is that in particular for FFT, the threads are relatively small, and so WaveScalar is actually able to pack more than one thread into a single cluster. And that means that when those threads communicate, they do so through the shared L1 data cache, so that communication is very, very cheap. So it's a combination of those 2 factors that account for that gap.
So you're actually doing the compiler analysis to figure out that these 2 thread instances are the things that are going to need to talk to each other and live in the same cluster?
So at least in FFT, it's more or less kind of all-to-all. They do these butterfly operations, and so you don't have to do that. In practice, though, I don't think that kind of information is taken into account by our placement system. It's certainly something that you could do.
Right. It seems like you only get that. I mean, it's just like normal cache allocation sort of strategies, right? You need
Right.
to keep them all stuff together, and if you can't deduce that, you're going to have somebody way over on the other side of the machine.
That's true. Yeah, this isn't a benefit that we'll see on all applications. I mean, there are also some applications where the working set is too large for a single cluster, and there we'll lose that benefit as well.
So you made a comment about FFT and very small threads.
Yeah.
And what I know about all your benchmarks is pretty small threads to compare to, say, something like, say, SQL, for example.
What was the example?
SQL?
Oh, yes.
I mean,
So you're worried about us blowing out the processor. So that is a concern. As I mentioned, caching is a problem. So we can do things like prefetching. That's a possibility. We're a little limited at the moment by our binary translator and the applications that we can successfully translate. I'll talk in a few more slides about some new research infrastructure we have that allow us to run larger programs and let us answer those questions.
so what would you say is the largest program in terms of threads?
Thread size, probably ocean or water. They're the 2 of the big splash applications. Oh, geez. I think
Order of magnitude.
ocean runs with 16 threads, so 8K in the working set, I think. Not sure. One nice thing about, in addition to prefetching, another thing that we can do is that because the WaveScalar execution model is very latency tolerant, it's pretty easy to imagine building kind of super WaveScalar processors by taking multiple cores and stamping them out and connecting them to one another. So that execution model still works fine, and so we can use that to buy more capacity. There's some other techniques that I can talk to you about offline that we've looked at for solving this problem also. Okay. Whoops. I'm going to talk next about some of the features of the underlying data flow. Go ahead.
Before we go on, just a question on the last section. So you were looking at the space of possible WaveScalar designs, and then using Splash 2 to evaluate which ones are pretty optimal.
Right.
How stable is that?
So
if you look at different applications.
Yeah, we did it across our whole suite of benchmarks. For the single-threaded applications, the curve goes like this. So you saturate pretty early. There's no single threaded program that we've looked at that can really utilize the 16 clusters in our larger designs. Some get a boost from having 4 clusters. For that area where there are Pareto optimal designs for both, for all the sets of workloads, there is very good agreement about what the good designs are. They vary in some very small details, but I'd say those are probably in the noise given our simulation infrastructure. Okay. So I'm going to talk next about some of the features of the underlying data flow execution model that WaveScalar uses to accomplish things that a conventional CMP simply cannot. And there's 2 pieces here. The first is an unordered memory interface, and the second is what we call mix and match parallelism. So the unordered memory interface is another set of instructions for accessing memory, and they live, you can think of them as living alongside the wave ordered interface that I talked about earlier. We provide it because the wave ordering interface is sometimes too restrictive. For instance, if you're writing something like matrix multiply, we have a lot of memory parallelism potentially. There's no way to express that in a conventional von Neumann instruction set or in the wave ordered memory interface. So we allow the programmer to circumvent it and manage the ordering or lack thereof among the memory operations explicitly. There's 2 new instructions, load unordered and store unordered, that allow us to do this. And we also provide a synchronization mechanism that allows these 2 memory interfaces to coexist in a well-defined way. We're also going to combine this with a fine-grained threading interface that allows us to profitably run threads that are very, very small. They just have a few tens of instructions in them. That turns out to complement this unordered memory interface quite nicely.
So, yeah, let me understand what this does. This is basically turning off all of the memory ordering stuff, and to use these instructions, your compiler is certifying that there's no aliasing.
Yep. Or where there might be aliasing, can insert data dependencies to order things properly.
So there are explicit, basically, thread synchronization level.
There is a barrier for doing thread synchronization for coarse-grained threads. There's also the store operation actually returns a value when its value has been written to memory, and that allows you to synchronize things otherwise.
You can fire these things out and then say, wait until this
Right.
particular one is done.
Right. So at this point, WaveScalar has 2 threading interfaces, this coarse-grained interface that I mentioned, and also this fine-grained interface. And it also has 2 interfaces to memory, this ordered interface and the unordered interface. So one of the nice things about WaveScalar is it allows us to combine all these interfaces in the same application, or even within the same function, to exploit whatever kind of parallelism is available at that particular point. And so we looked at one application from Spec FP to get an idea of how much that can actually buy us. So we looked at eQuake. eQuake spends 90% of its time in 2 functions. The first one is called sim. This is a bunch of easy to parallelize loops, and so the obvious thing to do here is to use coarse-grained threads. That's what we did. The second function is called SMVP. This has some trickier cross-iteration dependencies, and so here we've used fine-grained threads combined with our unordered memory interface to extract some parallelism there. Let's take a look at the results. So our single-threaded version is our base case. It gets a speed up of 1. If we just have the coarse-grained thread, so we don't have the unordered interface or the fine-grained threading interface, we can speed up sim, just that function, by a factor of 3.5. But because it's not the whole application, we get an overall speed up of just 1.4. For SMVP, if we just have the fine-grained threading interface, we can speed up SMVP by a factor of 11. But again, it's not the whole function, so we get a factor of 2.2 overall. But if we can combine the coarse-grained and the fine-grained threads and the ordered and unordered memory operations in the same program, we can speed up the whole application by a factor of 6. And so this is something you really couldn't accomplish in a CMP, exploiting all these different styles of parallelism in different parts of the same program, and have them all sort of live under this nice unified execution model. This is where WaveScalar really begins to shine. Okay. So to wrap up the WaveScalar portion of my talk, I'll just recap the WaveScalar's contributions, and these are actually the contributions of my thesis as well. So WaveScalar is a low-complexity data flow architecture. It solves the data flow memory ordering problem, and that makes it the first data flow instruction set, or architecture, to efficiently execute programs written in conventional imperative programming languages. It provides hybrid memory and threading interfaces and allows you to combine those very flexibly within a single function or within a single program. Provides scalable high performance. I showed you data that we could increase the size of the chip by a factor of 7 and get a commensurate increase in the level of performance. I also mentioned that it's the first instruction set to explicitly encode high-level structural information in the ISA. The last thing I'll mention about WaveScalar is that it's been an enormous amount of fun working on this group, or working on this project. It started off with just my advisor and I. As you can see, it's grown to be a pretty large enterprise. It's been a lot of fun watching the group grow, and it's also going to be a lot of fun to watch what happens after I leave. The most interesting aspect of that is this new hardware simulation, or hardware prototyping system that we've built. This is an array of 64 FPGAs. It's about 4 feet on a side. And what we're going to use this for is taking our RTL model and mapping it onto these FPGAs so that we can run larger systems and do larger system-level work. So we're going to boot an operating system. We'll be able to run these larger scale applications that'll be interesting. It's kind of a parallel effort. We have a real compiler coming up, so that'll help us in that direction as well. So this is going to be an enormous amount of fun to see what they end up doing with this, or what we end up doing with this. Okay. So the last bit I'm going to talk about today is moving beyond WaveScalar and how these technology trends that led us to look at an architecture like WaveScalar are going to lead to fundamental changes in all aspects of how we design computer systems. So the reason that this is going to happen comes back to this slide that I showed earlier. So back in the good old days, it was pretty clear how you wanted to design most computer systems. You should write single-threaded software and run it on single-threaded hardware. And this is a great state of affairs because as a single-threaded hardware gets faster exponentially, it means your software is going to get faster exponentially as well. After this inflection point, everything changes. And the architecture community there's a lot of work going in to looking at these chip multiprocessors. And that's great for architects because it's a pretty simple extension of what we already know how to do. Unfortunately, it leaves the programmers in a real pickle because programming these large-scale threaded systems is very, very difficult. We don't know how to do it. So as a result of that mismatch, there's going to be a bunch of interesting work going on in the next 5 to 10 years about how you build useful computer systems around CMPs and how you make all of that work. But I'm interested in taking a slightly different tack, or a pretty different tack. And that is to not presuppose that we should be building chip multiprocessors at all. And instead, to fundamentally rethink the roles that hardware and software play in the system, the interfaces that they should expose to one another, and how they should interact. So what I'm going to do over the next 3 minutes or so is give you 3 concrete examples of research projects I'm interested in working on in this space. And they're going to span a range. So the first one is a pretty near-term project. It deals with presently available technology, while the other 2 are a little bit more aggressive and go to how do we engineer these large-scale computer systems and also what it means to execute a program. So the first project is to make the instruction sets more expressive. So the key observation here is that modern programming languages provide an enormous amount of information about how the program is going to behave, and in particular, how it's going to use memory. Unfortunately, all of that information is lost because we can't express it in the instruction set, and that means that the processor can't exploit it. So on the architecture side, the question to ask is, what architectural mechanisms can we provide in the instruction set and also in the hardware itself to express and exploit the information that we already have available today? On the languages side, the question to ask is, what language constructs are most useful? Which ones provide the most useful information? And could we potentially tweak those a little bit to provide even more useful information that the processor can use to get better performance? So we've seen one example of this already today in WaveScalar's unordered memory interface, where by just adding those 2 instructions, we're able to speed up that one function, SMVP, in eQuake by a factor of 11. So the potential here is enormous, and I think there's a lot of low-hanging fruit in this area. The second project is to rethink the roles of hardware and software in the system. So the way that I think about it today is that the hardware provides services to software, things like an execution service and a protection service. But you can imagine broadening that interface and allowing it to go both ways, so that the software will actually provide services to the hardware as well. So one instance of this in WaveScalar is the instruction placement scheme that I mentioned, where when we need to place the instruction, we actually trap to the firmware and have it tell us where that instruction should go. That removes a lot of complexity from the hardware and also makes that placement policy very, very flexible. If you take this idea to its fullest extreme, you end up at this place where the CPU is just a process, along with the operating system and the applications that are running. And these processes provide services to one another. So the CPU still provides the execution service. The OS provides the resource management services, perhaps even managing the resources inside the CPU. And you can imagine applications providing specialized services to the CPU also to add functionality or to modify the way that the CPU behaves. The third problem is a search for new models of computation. So at the beginning of my talk, I talked about the von Neumann model and the data flow model as being sort of polar opposites. And here I've shown them at each end of a continuum. And you could label this continuum in a variety of ways. One is control-centric, the other is data-centric. One is centralized, the other is distributed. One is sequential, the other is parallel. And what's nice about these models is that in sort of their conceptual form, they're very, very simple. So on the von Neumann side, you start off with this very, very simple sequential model, but you go and you build a processor, and you find out that the performance isn't so good. So you try to find some parallelism by building an out-of-order processor, and you push towards this end of the spectrum. And as a result, the complexity of that processor increases exponentially. The same thing happened with data flow. So we start off with this very simple, very parallel model, but it's too parallel. We need some extra sequentiality so we can run our imperative programming languages. So we build A WaveScalar, which pushes towards that end of the spectrum and incurs additional complexity as well. So what we'd like to find is the programming model in the middle that can express the parallelism that we'd want to exploit while preserving the ordering semantics that we need to run the programs we're interested in. And the hope is that if you can find an execution model that lives there, a simple execution model that lives there, that its corresponding implementation in hardware should also be very simple and should lead to simpler processor designs. So there's a couple ways you can think about pursuing this. One is to build a communication-centric model. So it turns out that the cost of moving data across the chip actually dominates the cost of computing on that data in modern process technology. So perhaps communication should be the central actor in your execution model. You can also imagine a memory-centric model because memory performance is also very important. So perhaps that should be the focus of how you execute programs. So I'm going to leave you today with a final exultation that it's a really exciting time to be an architect. Technology trends have really sent us back to the drawing board, and WaveScalar is just kind of the beginning of the kind of things that we can start looking at now because everything has changed so radically. Fundamental changes are on the way in terms of how hardware and software interact, the large-scale system abstractions that we use to design large-scale computer systems, and also what it means to execute a program. The most exciting aspect of all of this are the opportunities that it opens up for collaboration between computer architecture and other areas of computer science. There's obviously work to be done in operating systems, compilers, and programming languages. Higher up the stack, issues of software engineering when we're looking at how we should construct these large-scale systems to take advantage of the hardware we can build. And even at the application level when we look at what sort of application support we should provide in the hardware itself. So if you're interested in this sort of thing, I'd love to talk to you either after my talk or later on during my visit. I think there's going to be an enormous amount of interesting work that's going to go on around this, and I think it's going to be a great deal of fun. That's all I have.